Welcome to this comprehensive guide on C-sharp memory management, a crucial aspect for writing efficient and robust applications. Understanding how C-sharp handles memory is not just about avoiding errors. It's about optimizing performance and ensuring your software runs smoothly, especially in demanding environments like the server rooms you see, where every byte counts and stability is paramount for continuous operation. Understanding how C Sharp handles memory is fundamental for every developer, especially when dealing with resource intensive tasks that require careful attention to system resources. As you type C Sharp code, knowing the underlying memory model allows you to write more performant and stable applications, directly impacting the responsiveness and reliability of your software, which is critical for a seamless user experience. C Sharp employs automatic memory management primarily through a sophisticated process known as garbage collection, which significantly simplifies development by automatically handling memory deallocation. This means developers are largely freed from the complex and error-prone task of manually allocating and releasing memory, allowing them to focus more on application logic and features rather than low-level memory operations. Garbage collection, or GC, automatically reclaims memory occupied by objects that are no longer referenced by the application, effectively cleaning up unused resources. When an object is no longer reachable from any active part of your program, the GC identifies it as garbage and frees up the memory it consumed, preventing accumulation of unused data and maintaining system health. This automated process prevents insidious memory leaks, which can degrade application performance over time and even lead to crashes, while also significantly reducing the burden on developers to manually manage memory. Unlike languages such as C++, where developers must meticulously track and deallocate memory, C-sharp SGC handles this complexity, allowing for faster development cycles and more stable applications. The .NET Runtime's garbage collector operates on a highly optimized generational hypothesis, categorizing objects into three distinct generations: Generation 0, Generation 1, and Generation 2. This intelligent design is based on the observation that most newly created objects are short-lived, while a small percentage of objects persist for much longer, allowing the GC to prioritize its cleaning efforts efficiently. Newly created objects are initially placed in Generation 0, which is the youngest and most frequently collected generation. This generation is designed to efficiently collect short-lived objects, as statistics show that a large majority of objects created by an application become unreachable very quickly, making Generation 0 collections fast and highly effective at reclaiming memory. Objects that successfully survive a Generation 0 collection are then promoted to Generation 1, indicating that they have a relatively longer lifespan than their Generation 0 counterparts. This promotion signifies that these objects are still actively being used by the application and are therefore less likely to be garbage, warranting less frequent collection scans. Similarly, objects surviving Generation 1 collections are further promoted to Generation 2, which contains the longest-lived objects in the application. This generation is collected the least frequently, as objects that reach this stage are typically critical components that remain active throughout the application's execution, such as static objects or long-lived caches. This generational approach significantly optimizes performance by focusing collection efforts on younger, short-lived objects, which are statistically far more likely to become garbage. By concentrating on Generation 0, the GC avoids the overhead of scanning the entire heap, leading to faster collection cycles and minimizing the impact on application responsiveness, making memory management highly efficient. The garbage collector is triggered automatically by the .NET Runtime when memory pressure is high or when certain predefined thresholds are met, ensuring efficient resource utilization without manual intervention. This automatic activation means the GC steps in precisely when needed, preventing excessive memory consumption and maintaining a healthy balance of available system resources for your application to run smoothly. One of the best practices for optimizing garbage collection performance is to minimize object allocations, especially within performance-critical code paths that execute frequently. Every object allocation adds to the GC's workload, so reducing unnecessary object creation can significantly decrease the frequency and duration of garbage collection cycles, leading to a more responsive application. Additionally, it's crucial to avoid creating large, temporary objects that can quickly fill up generation 0 and trigger more frequent and potentially more expensive collections. Such objects, even if short-lived, can cause the GC to work harder than necessary, leading to performance hiccups and increased CPU usage as the system constantly cleans up these transient, memory-intensive items. Another powerful technique for proactive memory management, complementing the garbage collector, is object pooling, which focuses on reusing expensive objects instead of repeatedly creating and destroying them. This strategy is particularly effective for objects that are costly to instantiate, as it avoids the overhead associated with their creation and subsequent garbage collection, leading to significant performance gains. Object pooling is particularly useful for objects that are inherently costly to instantiate, such as establishing new database connections, opening network sockets, or rendering complex graphical elements. These operations often involve significant I/O, resource allocation, or computational effort, making their repeated creation a performance bottleneck that pooling can effectively mitigate by recycling existing instances. The primary benefits of object pooling include a substantial reduction in allocation and deallocation overhead, directly leading to improved application performance and significantly reduced GC pressure. By reusing objects, you minimize the work the garbage collector needs to do, resulting in fewer and shorter GC pauses, which translates to a smoother and more responsive user experience for your application. A simple object pool can be effectively implemented using concurrent data structures like a concurrent bag or a queue to safely store and retrieve available objects across multiple threads. A concurrent bag offers unordered, thread-safe access, while a queue provides a first-in, first-out mechanism, both suitable for managing a collection of reusable objects without introducing complex locking mechanisms. The operational flow is straightforward. When an object is needed, it's retrieved from the pool. Once its task is complete and it's no longer needed, it's returned to the pool for future use by another part of the application. This borrow and return model ensures that a limited set of expensive objects can serve many requests without the constant overhead of creation and destruction. This approach is ideal in scenarios where objects are frequently created and destroyed in rapid succession, such as in high-performance game development for managing bullets or particle effects, or within high-transaction systems like web servers handling numerous incoming requests. In these contexts, object pooling can dramatically reduce latency and improve overall system throughput by eliminating repetitive object instantiation costs. Finally, let's explore weak references, a more advanced and nuanced concept that allows you to reference an object without preventing its garbage collection, offering a flexible approach to memory management. Unlike standard references, weak references do not keep an object alive in memory solely by their existence, providing a mechanism for optional object retention based on memory availability. Normally, a strong reference, which is the default type of reference in C#, keeps an object alive in memory, preventing the garbage collector from collecting it as long as that reference exists and is reachable. This strong connection ensures that an object remains available for use as long as any part of your program actively holds a reference to it, guaranteeing its presence. A weak reference, however, allows you to access an object if it's still alive and hasn't been collected, but crucially, it won't prevent the GC from collecting it if no strong references exist anywhere else in the application. This means the object can be reclaimed by the GC if memory pressure arises, even if a weak reference to it still technically exists, making it a non-owning reference. This characteristic makes weak references particularly useful for implementing caching mechanisms where you want to store objects for quick access, but also allow them to be collected if memory becomes scarce. It provides a graceful way to discard cached data when system resources are low, prioritizing overall application stability over the immediate availability of cached items, which can always be reloaded. Weak references are implemented using the weak reference T class in C#, which provides a safe way to interact with potentially collected objects, allowing you to check if the target object is still available before attempting to use it. You typically use the try-get-target method to safely retrieve the object, which returns true if the object is still alive and false if it has been collected. They are ideal for scenarios like managing large image caches or metadata stores where the data can be reloaded from its original source if necessary, rather than holding onto it indefinitely. This approach prevents the cache from consuming excessive memory and potentially causing out-of-memory errors, ensuring that your application remains responsive even under high memory load by selectively discarding less critical data. In summary, C-sharp memory management is a multifaceted topic that relies on three core pillars: garbage collection for automatic cleanup of unreferenced objects, object pooling for the efficient reuse of expensive resources, and weak references for flexible, memory-sensitive caching strategies. Each technique addresses different aspects of memory optimization, working together to create robust and performant applications. Mastering these fundamental concepts of C-sharp memory management will significantly enhance your ability to write high-performance, memory-efficient, and stable C-sharp applications. A deep understanding allows you to diagnose and prevent memory-related issues, leading to more reliable software that performs optimally even under demanding conditions, ultimately improving the quality of your code and user experience. Thank you for watching this guide on C-sharp memory management. We strongly encourage you to explore further resources, delve into official documentation, and experiment with these concepts in your own projects to deepen your understanding. Continuous learning and practical application are key to becoming proficient in optimizing your C-sharp applications for peak performance and efficiency.